Okay, so I want to give an important application of the feature regression model, and that is the random feature regression model. And this is very simple. All you do is you take the features, and instead of sort of handcrafting some nice features that mean something, we're going to choose the features randomly. So for each phi I, those are the features. The way I'm going to construct them, I'm going to define phi I of x to just be, for example, I could take the inner product of the input x with some random vector. So I pick some fixed random vector yi for each I, and this is all for every feature I have. There's n parameter of them, and I do the inner product. So this is a random feature with by taking the inner product with a random direction. And if you want to make it nonlinear, you can apply some nonlinearity everywhere. So I'll do some function phi from R to R. This will be some nonlinearity. And more generally, you can just pick a function randomly from some space of functions. But this is one concrete example. And when you do that, that's called the random feature regression model. So you apply the same thing we did before, and now you have these random features. And the nice thing about choosing them randomly is you can make NPAR as big or as small as you want, because there's no problem to make more or less features. You just choose more or less random variables. When you do it, what you end up with is this kernel, k of x prime. And we said in the previous videos that this kernel is the thing that determines the whole model. It drives the bus. You can write the final answer down in terms of the kernel k. You can write all the distributions down in terms of the kernel k. K contains all of the information about how the features are affecting the problem. So the features themselves don't matter. What only matters is the kernel k. And the kernel k is defined like this. It's 1 over NPAR times the sum I equals 1 to NPAR of phi I of x, phi I of x prime. So you take two independent things and you apply it at x, you apply it at x prime, and you sum over all the possible features. So the important thing is, by the analysis we did before, the individual features don't do anything except for how they appear in K. The only thing the model sees, so to speak, is the kernel K. And this is the beautiful thing. If you do the random features model, so let's put in our formula here. So in the random features model, this is 1 over NPAR, sum I equals 1 to NPAR, phi of the inner product x with yi, phi of x prime with yi, and you have this big sum. Here's the beautiful thing. If these things are random and independent, then what we have here is a sum of NPAR independent random variables. So this is the sum of NPAR independent, and the yi's all have the same distribution, so they're independent and identically distributed random variables. So if you do the random features model and you make NPAR bigger and bigger and bigger, you are summing more and more independent and identically distributed random variables. And not only are you summing them, because of the funny square root factor we put in the original model that translated to this 1 over NPAR in the K, not only are we summing them, we're also averaging them. So as you make NPAR bigger and bigger and bigger by summing up more and more of these random variables, you're ending up with something that is getting closer and closer to the average of the random variables. And in the limit that NPAR goes to infinity in this random features model, as you make the number of parameters go to infinity and the number of features go to infinity, you're going to have some wacky thing with many different crazy parameters and many different, the features are going to go wacky, but the kernel is going to settle down. And the kernel is the only thing that matters for the behavior of the model. So in this limit, that the number of parameters goes to infinity, that even though the features themselves, you're getting more and more of them, and perhaps they're all doing something wonky, the kernel K is the average over all of them. And as you average more and more things, the kernel K settles down and becomes something nice. And in fact, it converges to the expected value of phi of xy, phi of xy, averaged over whatever distribution of y you chose. So in the random features regression model, the nice thing about the random features regression model is as you increase the number of things in it, it becomes more and more sort of, the kernel K becomes less and less random. The more randomness you add to it, the less random K becomes. And in the limit that the number of parameters you're using goes to infinity, it settles down to this deterministic thing, and involving an expectation that looks like this. And for a neural network, this also happens. So this like sort of explains why very wide neural networks behave in a way that you can understand, where you can't understand a narrower one. And it really has to do with this kind of thing. And I'll give one example, one particular example of a random features regression, which is a last layer only neural net. Let's do that in another vid though.